All right.
Hey, yay.
I just want to thank everyone for being here today. Last time, my first Camerimage was last year, so I got to sort of experience what everybody had been telling me about. And yes, I also got sick, so that was kind of fun. This time around, I realized it would be really cool to get into like the weeds and get a little technical. Within Atlas Lens Co., we like to really share what we've learned and what we've seen to improve our processes, or whether that's design or manufacturing. And today we have Scott DeWald with us, who's our chief optical engineer. And I'm Forrest Schultz, president, co-founder, and lead designer of the engineering team. And so this is kind of my favorite part, because I get to just sort of be a nerd, and you just have to follow along with all of that. And so before we get too far in, I just want to show you guys kind of what's coming up during this presentation. So we'll go through a few introductions and background here of Scott and myself. We're going to talk a little bit about the design considerations for digital sensors, the fundamental principle of just anamorphic focus and why it's a challenge in general, and then specifically for Atlas Lens Co., our journey into our first optical design, which was the Orion. That's what we have on the camera here. So in a little bit, we'll also do some live discussion about the image and sort of characteristics that we see in it from the presentation. Also, we're going to talk about the Mercury design and share a lot about its architecture, how we got to that point from the early days until what we have here, which is now a patented design. We're going to talk a little bit about the optomechanical process, which all of our mechanical engineers, they're not here right now. They get to go to Cine Gear and stuff, but I'd really love for everyone to experience this one time, because I know they'd love to be here with everybody. And one of the things I want to say is that I really appreciate my team. I get a little emotional sometimes. So
Top people, though.
They're really cool. Everyone's really good. And I think about them, so when I'm not here, I'm kind of just like, I kind of feel split, because I want to engage with them and answer questions for them. But they are really carrying the sword, and they're able to continue everything that we're doing back in the R&D side of things. So I just want to give them a shout out. We're going to stick around, because towards the end we're going to share a little bit of a surprise. We brought some stuff that's kind of fun, a little bit of rough and raw things that we're building. And usually we wait a while to do that type of stuff, because you kind of want to perfect it. You kind of want to say, hey, this is what's coming out. But we thought, why not just take you along for the ride and literally show you where we are today, so that you can get a glimpse a little bit into the future. We'll also put that up for some live camera demonstrations, see if we can make that work. And before we fully get started, I'm going to switch over real quick to a little show reel, so we can kind of jazz up and see what these lenses were designed for. I forget that they're not just this really beautiful looking instrument and tool that I get to stare at all day on a computer or work on physically, but really they're meant to create things. And so when I see what people have created with them, I think that's really the biggest reward. So I just want to share that with you all.
for my close-up now.
All right. Thanks. All right. Oh, and we will have a Q&A, and we want to save a lot of time for that, so I'll hand it over to Scott to introduce himself.
Right. Yeah, quick introduction. Scott DeWald. I've been a consultant for a while before I started to work with Atlas. I started out as actually a rocket scientist at Hughes Aircraft, and when the space shuttle blew up in 1986, I had to find different work. And that kind of led in a circuitous manner to getting into the optics business. And I've had quite a varied career, as you can see. I was at Texas Instruments when the DLP project was getting started. In fact, the projectors technology, pretty much all of it was developed when I was there in the 3-chip business. And this is interesting. On the left is me in 1997 at screening room at Paramount Studios with the first prototype DLP cinema projector that was put together on an optical table wherever we put it. And it was using a SXGA 5x4 aspect DMD chip that needed to be stretched anamorphically to, no, keep it there, to do either CinemaScope or Academy 185. And that big black lens in front of either one of those is the first anamorphic lens I designed. It was interesting is that back in Paramount, I have to give them credit because they were instrumental in the development of DLP cinema. And we actually shot out against film in that screening room over and over again for a year and a half. And cinematographers came in to look at their footage in this environment, including I didn't know at the time who Gordon Willis was, but he was actually watching some of the Godfather clips that we shot out against digitally versus film. Here's another picture of one of the giant ISCO anamorphic lenses. You can buy them off of eBay. I think about 150 of them were built for the first rollout of DLP cinema.
Awesome.
Yeah, it's, what's the next slide?
Okay,
it's you. Okay, yeah, it's pretty much, you can ask me more questions later. But,
yeah. So I'll go to the next. My background's very different, not a rocket scientist, and I want to say first, I don't think I got to include it here, but Scott's been a huge mentor to me, whether he knows it or not. Everything he's shared with me from the beginning, I've secretly been absorbing it all like a sponge. So prior to that, prior to Atlas, really, just basically straight out of high school, I got into composites because of a job that I went to a company that makes boats. My neighbor got me that job, and at first everything just looked like a mystery to me. I didn't understand what I was looking at, but something really changed. I think maybe it was always a little bit there, and I'll get a little bit into that, but something kind of clicked in my brain that I really enjoyed the process of solving these types of challenges, and it was a mold-making tooling room, so we designed and built basically what was going to be the holes and also the interiors of these boats, and they're like the sporting style ones. So you'd have to kind of think in reverse. You would do layups with carbon fiber, or fiberglass really was what we used, and polyester resin, which had like a sweet stink to it, which I really kind of enjoyed. There's something that gets in your blood, so I guess. But I went from that to getting into sculpting and just kind of pushing out some things that I really liked as far as movies at the time, like The Dark Knight was really intriguing to me, and there wasn't anybody doing really good replicas at the time of these props. Now cosplay and all this stuff is very popular. I think back then, though, I didn't really even know there was a word for it. But what I was doing was trying to replicate what they would do for the movies, so I actually learned all those processes of silicone mold making, which got me into 3D printing pretty early on when stuff was way too expensive compared to now. I paid like $3,000 when it should have been, now it's $300 to get that printer. That led me into what I really always enjoyed was, as a kid, movie making, and mostly it was a hobby, an outlet for me. It's more about the, just if I feel like doing it, it felt like I need to do this to express something. I started wanting to shoot anamorphic, and I got to the point where I realized that's just not cheap to do. There was definitely some vintage stuff I could use, but it didn't seem to satisfy the looks and stuff I was going for. So I started buying a bunch of stuff from Surplus Shed and other optics and bashing things together. So kind of what you see playing in the background is just like a really boring test of me just filming a ladder or something like that in the background. But it's actually a focusing Anamorphic, which was built off of a Rokinon sitting on top of a Blackmagic pocket camera. And this test for me was kind of unique because it was a 1.3x squeeze, but I was getting a lot more bokeh and stretch out of it, which just kind of fascinated me. And I really wanted to understand what principle was going on there that allowed me to do that. And so I downloaded an app on my phone, which was just a ray tracing app that allowed me to sort of replicate and put these lenses back into it. And that kind of just linearly led to sharing these tests online, meeting Dan Keynes, who co-founded the company with me, also meeting Scott. It all kind of happened around the same time. We found Scott, had a phone call with him. I'd show him some stuff I was doing. He'd make fun of me, and no, not really, but we'd look at it together and talk about it, and eventually these ideas, these things turned into ultimately what was like, let's build a prime anamorphic. We have to design something. So that got us over to discussions about designing the Orion series. Mm-hmm.
So
go ahead.
You're starting from scratch now. If you were to design a lens based to be used with digital cameras instead of film, what would you do differently? And I'm going to point out a few of the differences. Obviously, film has a bunch of different size grains. They give you the wide latitude and exposure. The larger grains are more sensitive to light. But it's a completely random system, and the resolution drops off very slowly. Versus on the bottom, you see very common on the left is is a common bare pattern digital sensor. And generally, you have half as many blue pixels in red pixels as there are green pixels. So it's more important to get the green resolution to be corrected better than the other two colors. And what's interesting is this is just for the sensor itself. Then you have on top of that, you've got the optical low-pass filter, you've got chroma subsampling, you've got compression. So there's all these other things that that take the red and blue colors resolution to be lower than the green. Now on the right is even a more modern sensor. I don't know whose this is, but they're interspersed white pixels, and the white pixels are much lower noise. So you can get, that's how you get 14 stops of depth of dynamic range, I guess. So the white pixels get the low noise section, and the green and red give you the chroma, and the computer puts it back together. And it's a really interesting technique. Go ahead. And another thing that we did differently was we optimized around the P3 color gamut. I forgot to mention earlier that when I was at TI, the P3 color gamut was proposed to SEMPTE based on some designs that we were doing. So if you don't like the P3 color gamut, you have to blame me, because I was the person who submitted it to SEMPTE. So it's a little bit more difficult to use the P3 color gamut for designing, especially with the lead-free glasses nowadays, which have a lot of dispersion in the blue. The other thing about the modern glasses that are lead-free is they have more absorption of the blue, so it's harder to make a cool lens. Everything has a warm look to it, because sometimes 8 to 10% of your blue light doesn't make it through the lens. So that was our philosophy when we were designing, is P3 color gamut, dealing with the aspects of digital sensors and how that information is treated differently than film.
Yeah.
Go ahead, Tix.
Yeah. The next one.
And then, so the other thing that is different is generally, well, almost all digital sensors have glass in front of them. Usually that glass is thin, but then you also have optical low-pass filter, you can have ND filters, you can have an IR sensor, and suddenly you've got 3 or 4 millimeters of glass. And if you were to take a lens that was designed to work perfectly in air, like is shown on the left, and you make it go through 4 millimeters of glass, you lose some resolution. So it's spherical aberration essentially. So you need to correct for that. And what's interesting is if you use a lens that's designed for a digital sensor on film, it actually works pretty well, but it doesn't work as well the other way around, just the way spherical aberration correction works.
Yeah. And one of the first things I kind of wanted to get into as far as the sort of the why of it was with anamorphic focus. A lot of questions, or a lot of times people ask, can't you just move, the lens? What makes it more challenging than a spherical? Like, can't you just take the lens base and shift it forward? And that's commonly, that's one thing that you have to solve for. And I just wanted to see if I could quickly get this out there so that people can kind of grasp that with me, because it took me a long time to sort of pick that apart and see what the challenge was there. But essentially, you're dealing with two effective focal lengths. I'll hold this up too. But on the screen there, we have an image of like a cylinder. And you can imagine, of course, light doesn't care where it's going. It's just going to go everywhere. It's going to fill the pupil of the lens. But to simplify things, what I've done here is I've drawn, let's say, a line, or a plane, right, in the vertical, which is that red plane, and then a plane in the horizontal. That's to describe the powered axis of where the cylinder is. And so, because we're going to analyze both of those planes of focus, essentially, to describe what the dilemma is here and why we could end up with astigmatism if we don't correct for it. And so with both of these drawn here on the screen, you can see on the top that we have a perfect harmony where the cylinders, which are the first two elements in this diagram here, and then you have a rotated view so that you can see the non-powered axis. That in that plane, those cylinders are just acting like windows, just straight glass.
Yeah, so I should point out the top picture is a top view of the lens, and the bottom picture is a side view of the lens.
That's correct. And here they have the same conjugate focus because they're both focused at infinity. And a lot of people have done this. If you've bought like an adapter or made one yourself, this is basically the first step that everyone does. Is they'll take like a projector lens that was anamorphic, like one that Scott had mentioned before, put it in front of a prime lens, and you can get it to focus at one position. You could either choose infinity or some other one. The problem comes is when you move the object. So, and the infinity position, that's just a repeat of the previous. Now we've gone to the close focus, and this is, if I toggle back and forth here, you can kind of see what's happening. We're just moving the rear lens to try to focus on something closer. It's achieved in one direction, but that's what you're going to get, is you're going to get, basically, things are going to turn into a sharp line in one direction, but then they're going to stay defocused in the other. And you won't be able to fix that unless you do something new. Lomos, square fronts, let's say, they'll move one of the actual primary cylinders to accomplish focus. And I have an example of that sort of drawn up here in ZMax that we wanted to pull through real quick. But on the bottom there, that's the disparity. You have astigmatism where you don't have them falling on the same plane.
The separation of the two focal points, the green and the blue and the red.
Correct.
That's the astigmatism that you have to correct.
You want them to both land on the farthest point back, which would be the sensor plane.
Right.
Yeah. But the sensor plane isn't going to move for you, so that's stuck on your camera. And even if it did, you can tell that there is no point in which those two would ever come together. So something new has to happen or be introduced. Like I said, one of the simplest methods is to try and focus the cylinder. So in the first example here, we've just recreated that same setup where on the top, we got the top view down. On the bottom view here, the bottom right, it's the side view. We have an image simulation that's in black here, and on the top is a spot diagram. You can barely see it, but there's a very tiny spot there, about 1 micron in this example. This is just green light, so I turned off the other colors just to kind of keep it more simple for the graph. So this is at infinity. This is what I was talking about when you move the object to, say, 1.6 feet or 500 millimeters, half a meter. If you try to do that, you're going to end up with this. And we've all probably seen a little bit of this, but astigmatism can show up in big ways like this, where it's just super obvious. You would never want to look at that. You wouldn't show it. But oftentimes you're left with a little residual astigmatism due to things like calibration, due to things like the timing of your lens. Even in a perfect design, some little bit amount of this might exist in your anamorphic system. This is what happens now if we move the cylinder. So I'm just kind of toggling back and forth with close focus, and we move the cylinder. We've achieved focus again, and it's not super obvious, but what's happened here is we've created mumps. And mumps is just the loss of squeeze factor from one focus position to another. So at infinity, let's say this example, we were at a 2x squeeze. We've gone down to now maybe a 1.7 squeeze or something, and that just wouldn't be acceptable. When you de-squeeze that, you don't have a variable squeeze ratio capturing what you're doing with your focusing. at least not commonly. And that was an old problem, and that was a problem that was solved when companies started picking up on that and trying to create solutions that compensated for this.
The internal astigmatism creation.
Yeah. So you either have to put in an internal compensator. There's solutions like the rotating counter stigmatizers. And there's also one other, which is what we call the variable diopter system. That's what we adopted for doing the Orion. One of those reasons was because it kept things kind of simple, especially for our first anamorphic.
Yeah.
And it was a tried and true method as well. So it's something that has existed for probably at least 100 years now, if not. So we kind of went through our options, and we figured that would be one good approach to do that with the Orions. The one disadvantage there is that you have to keep the chief ray and its size considered. So your lens can kind of get a little big especially if you're doing larger formats or longer focal lengths. You're going to have a sizable amount of glass in front of your anamorphic group. But you get a few characteristics that also aided us in our design choices, which was we wanted the Orions to have a classic look. We didn't want that lens ever to appear like a modern, hyper-corrected lens. And for that reason, I feel that we kind of landed on that together. It was our first sort of venture into doing this, and Scott led most of that way because he had the most experience at that time to lead that. Do you want to share anything about the Orions?
Well, we had, is the trade-off slide after this or not?
Oh, let's see. Oh,
Guess not. All right.
Oh, actually, this is just to explain what I was just saying.
Right. So this is the variable diopter effect, right? And there's design trade-offs that have to do with the size of the lens. Go back.
Yeah.
And close focus. The closer you want to make the focus, the stronger those two elements in front have to be, or they have to move further, or they have to get bigger. So there was one trade-off after another. Well, with distortion. Another thing is the closer focus you make it, the more power also creates more spherical aberration, so the lens gets softer as you get up front. Here's a kind of an explanation. Yeah,
Infinity on the left and close focus on the right.
Right, so it's pretty obvious on the right half of each of those pictures. You'll see a blue line and a red and green line on top of each other. I don't know. Oh, where's the cursor working?
I think, can you guys see that? Yeah, you can.
Yeah, all right.
Okay.
We'll go off to the left.
Yeah.
Yeah, there we go. See, that's actually well corrected, except for axial color.
We should explain. You want to see everything
everything in a straight line.
Laying on
horizontal.
The horizontal line would be perfect.
Right. So here you can see the fifth order spherical aberration in green and red, and then as we go to close focus, you can see this third order spherical aberration is created, and that just makes it less sharp as you get to close focus.
And this is, we all know this, but this is a wide open, and you can kind of see something interesting happening where the red and the blue are well corrected for a little bit, but then you kind of see it tail off. The blue
takes off.
As you'll see a difference when you stop the lens down. So these rays are presented from the on-axis, so we're looking
right down the center.
The ray bundle that passes right down center. The next slide here shows an example of if you take the same Orion lens. So this is based off the 65 millimeter, which we have here on the camera. And if you take it wide open, you'll see a lot of that blue trailing off, but if you stop it down to 2.8, you've removed that
a lot of that halo of blue.
That sort of 2/3 area outside of the aperture.
But remember that blue pixels, there's half as many blue pixels, and it's compressed even more in subsampled, so it's not as critical to the resolution of the image as you would think.
That's what Scott says, but no. I'm just kidding.
Well, it's digital now.
Yeah, no, but it's cool to see that, because when the more we do this, the more we're able to translate what comes off these graphs and what you see on the camera, what you see on the projector. Now that we've built up a library of different focal lengths, different lenses, and now the Mercuries, for example, it's really cool to be able to refer back to this material and find the correlations and use them. So we have in summary for the Orion series, one of the main reasons was mechanically it is easier to implement. In theory, because you're only moving, let's say, one group or one element in certain cases. We also have a constant anamorphic ratio. One of the problems that I brought up earlier about moving the cylinder, you don't have to do that in a variable diopter system all of your focusing takes place before it ever even enters that lens.
The cylinder.
The lens doesn't even know that it's refocusing. You're doing it by changing the power of those optics up in the front of the system. You do get a change in focal length,
yeah.
which causes breathing. The interesting thing about the Orions, though, is it breathes sort of in the negative manner. So you get a shorter focal length, which means you see more of the room as you focus. Let's see how quickly. Can we swap to camera real quick? Oops. Ooh, that was probably me, though. I'm electric. Is it on? Oh, cool. So I'm just going to use the audience here, you guys as an example. So that's actually close focus. We'll start here, sort of far out. And just sort of watch the field of view as I rack focus onto my best here, but a lot, it's kind of coming in. So you'll see people on the edges that weren't there previously in frame. Now I'm going to make them disappear. So you still do get a disparate sort of squeeze and breathing, but you do get sort of an increase in field of view. This lens being 65, maybe it's less pronounced, but you guys can capture that there. I find that one kind of pleasing. Other types of breathing I can find a little distracting, especially if you get too much of a zooming in and out. Here's one of our newer lenses, the Orion. I wanted to show a bit of, thank you, forgot to pass. The optomechanic design for the 200 was a little unique in the sense that we had to come up with a few solutions. One of them was driving an optic that's very much way up in the front of the lens, but keeping the positions of the cam and basically where the gear is and where the bearing is in a traditional spot where it would just make more sense for us to manufacture it that way. And it's a pretty heavy element because it's quite big that we wanted to make sure there was no image shift or no racking when you would change directions. And our team did a really good job of figuring this out. We sort of spread let's say the moment between near where the lens is sitting, and then we have an area that's also concentrated at the back so that load is shared between those 2 points, and there's just really no way that lens is going to ever want to tilt forward. And some other designs, you might have just a small section moving, but that could cause some image shift and racking.
And that's what allowed the 200 millimeter to focus down to 3 feet, right?
Yeah, the 200, 3.5 feet. Yeah. But for a 200, that still looks really close. This is one of the
parts in there, yeah.
Yeah. Bradley took the lead on making this one look really cool. I kept pushing him to skeletize it more and more. I said, "Look, we gotta shave weight, so let's make this thing." We went real extreme, and then we backed off a little bit, just because I think we went a little overboard with how much we hollowed it out. So this was our compromise together. It still looks pretty cool.
We followed up the Orion with the Mercury series.
Well, yeah. There's a lot of stuff with I'd love to go into more, but for the sake of time,
questions,
we're going to go to the Mercuries now. That way we can keep on moving forward. But there's the wide-angle Orions, which have a few more elements up in front, and that's what helps it achieve such a wide angle and extreme field of view. And impressively, I mean, they maintain really good focus and bokeh characteristics throughout that as well.
Yeah, we use the same design philosophy of the whole series, so they look kind of the same.
Yeah, actually, at the beginning here, I'm just gonna be real cheese. Boom, 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 boom. Oh yeah, it's this faded image of that. That's the 25 millimeter, so you can see the 3 elements. One of those is the focusing element, and the other highly negative elements help contribute to its
short focal length.
Yeah, it's huge field of view, basically. All right, back to Mercury. Mercury uses a different focusing method because back when I was, lens bashing and doing that stuff in the kitchen, I think even maybe one of the pictures I had on there, I came up with this method which I just wasn't finding in the patents anywhere. I also studied a few patents just to get ideas from. And one that I couldn't figure out why it wasn't being used was using a compensator that didn't have any cylinder power in it. I found a lot that needed cylinder power, but I thought, well, what if I could simplify and just use a spherical compensator?
And I told you it wasn't going to work.
Yeah, Scott put me off a few times because he's like, no, that's impossible, you know. And I thought, well, let's figure it out. But one thing you can do in ZMAX is you can set up paraxial lenses, and if you can solve for it paraxially, then you know that by nature it is possible, and so you have the sort of first order optics allow it to happen. And I think that's all you did to convince yourself, right? You finally listened to me. No, I'm just kidding, but. So I knew it worked because I did it in person, right? So no one's going to tell me I didn't do it because it's like I saw it happen. And what I didn't know was how well it would correct for it. I think we were both surprised about that. Yeah. I thought it was just going to create sort of a fun, look. Maybe it wasn't going to be super usable, but what started as, okay, well, let's try it. Let's see how far we can push this design, turned into this design here, which was our first one, the 42. We did go through a few prototypes. This is ultimately the one that we landed on. So that design that you see on the screen there is this one cutaway. And it uses a now patented compensator method, which is just the coupling of the rear spherical movement with the compensator. But it is no accident. There is there's a high degree of math involved that helps you understand how that works that Scott was able to figure out. I just let ZMAX tell me what it needs to do. But we ultimately got to a point where we could solve for not just one focal length, we could solve for wides, for telephotos. And here's another view of the focus going back and forth. So we have the rear group you can see move. When I say the rear group, I mean
group's all spherical.
All of those spherical elements that are small in the back. You have the two cylinders that are separated.
And they're fixed.
The unique thing, too, is that there's a high degree of color correction, but there are only two cylinders in this design. Typically, you'll see cylindrical doublets being used to offer a lot more color correction, probably for lateral color. This has a high degree of lateral color correction as well as very, very good on-axis color correction. I didn't actually prepare anything about that, but there's a difference between longitudinal color aberration, which is usually what people don't like when you see fringing right in the middle of your scene. So anything near the center that's color aberrated is axial. It's going to be longitudinal. Stuff that's at the corners or on the sides, if you see it sort of spreading out, like separating from itself, like a rainbow effect. If it's like sort of next to each other, each color is sort of segmented, that's going to be your lateral color. And this corrects pretty well for both of those. And Scott, I don't know if you want to talk about that.
Yeah, this is kind of the stuff that was in our patent application, where just to show you, this is a stylistic version of what's going on in this. Oh, yeah.
Yeah, go ahead.
Yeah, what's going on in the. So, this is that negative cylinder in front. This is the positive cylinder. This is the compensator here. This is the big spherical group in back. So there's all these distances. There's individual focal lengths for each one. Let's go to the next. Yeah, there you go. So essentially, this is from the patent application also. We've got 10 variables, and we have 6 equations. Here we try to keep the focal length close, both near and far. We want to keep the back focal length exactly the same near and far. And you see the matrix equation there. I actually tried to solve this myself. It took me a whole day, and then I entered it into some AI thing, and it went and did it. And I only missed one minus sign way down here at the bottom, but obviously no one's going to try to do that. But you can stick that into a computer program and just let it pick. They said there's an infinite number of solutions, but there's only a fixed number that involve all positive distances, which is kind of important. So, this is why it works. It was bugging me for a year until we were writing a patent application. We have to explain to these guys why this works. So this is the neat stuff, I guess, to me.
Yeah.
Great.
Yeah, very good. Thank you, Scott. Oh, wait. Ooh, okay.
Uh-oh.
That's our sign. Let's do that again.
Yeah.
Ready?
Yeah.
Okay, so let's go to the camera real quick and put on the Mercury. I want to do a couple Mercuries real fast. Anyone who's shot on the Orions knows that they do sharpen up when you stop them down. As we explained, it's the fifth order spherical aberration kind of going away, as well as that trailing off blue. You get better focus. But with the Mercuries, they were designed to have a lot better center performance and a little bit, we sort of relaxed on the horizontal fall off, so we allowed them to have a bit more portrait effect. Yeah, Hajun, if you could come up, that'll just make it easy. So, oh yeah. Oh, right, thank you.
Yeah, got to change the aspect.
Smart. It is a different, you can do it from there? Yep. Okay. Thank you so much. Can you stay for a second? I'm gonna focus on you. Come close. Closer. Up to the light. There you go. So what I wanted to show here was there we have the 42, and as you can see, there's a lot of cool things about it. Some of that is sort of this pencil effect, right, that we have going on in the edges, the pronounced sort of distortion. But if I even focus in those areas, if I go back to the audience, you'll find that there's going to be a different degree of center focus versus those the audience members here on the edges of the screen. Oh, cool. I like that. So also, these ones flare warm. The Orions were designed to be sort of the traditional mag fluoride blue coatings. These ones have a warm flare. I really like that. And thank you, Hajun. I just wanted to have someone close up. There you go. Can I put on the 27 and you stay with me? Sure. All right. Actually, this one could work with two people. Is there someone in the audience who could come up with Hajun and do it and get on camera?
I believe it.
Awesome. Thank you. So we just, I brought this with me on the plane. We finished it this week. Was it this week? Last week.
Last Friday. Yeah.
I can't remember now. 2 days before the coming here, we got the 27 ready. It involved a little bit of a last-minute hustle, but we were able to get the optics working, calibrated, make sure it's wide open. And so with the 27, you can see the big difference in field of view. Also, a little bit more distortion. So I'm going to kind of pull over here. Same sort of flares. Now this one, because it's a prototype, it is uncoated. One of the optics is uncoated, so there's a lot more flaring that will probably be reduced, but I'm going to focus on the audience now. 2.2, and the 42 is also 2.2 as well. So really bendy table, as you can see, but beautiful subjects. All right, very cool. And then let's see, close focus. Apologize, Hajun. And your name?
Max.
Max. Thank you so much, Max. All right. And like I said, so I can't really see if I can see this now. If I stare in, I mean, when I talk about these things like the extra fall off, I think these are things that if you pixel peep, you'll see them. But for most people, it's sort of what they'll describe as that's kind of like the character. It's just enough that you're not going overboard with it. And from our standpoint as designers at Atlas, it's always been important to us to come at this from sort of a cinematographer's point of view and not just try to hit, things on a piece of paper. Going back to why I'm very proud of the team, I'm proud of everybody, our marketing team, sales, logistics, everything. Everybody contributes because everybody is a creative at the company in their own way. And they've all contributed, whether they know it or not, to helping complete the looks of these lenses. So, all right. No. I won't delay anymore. Ooh. We brought something that was kind of like, should we bring it? I think on the last day we decided, yeah, we can do it. If you guys know what astigmatizer-based focus designs are, we have been working on it. And it's halfway working, so we're like, let's do it. Yeah. It's really grand. So for you that are in the back, Hajun helped me take some pictures earlier. We thought, hey, I could, instead of having the key shot up, let's just take the pictures of it now. So the design, the family like of Gemini is meant to be a 2x series of anamorphics that yet to be determined how large of format we're going to go. So we want to give the 2x platform back and give everybody some options. Let's see, we'll go back to 2x mode, right? 8K? Yeah, 8K.
Now, this is not a classic focusing system. This is another new version of the deastigmatizer system that we have filed a patent on. Also.
It is a unique approach on, although that phrasing, right, the stigmatizer-based focus, maybe people know it, but we found a unique approach that has not been used, and therefore it is patent pending. And in the process, just to give you guys, to be real with you guys, like the insight is it's very difficult to produce some of these optics because they're very low power, and the nature of doing some of these in a repetitive manner, or to get them repeatable, it requires a lot of precision, and we're moving forward on that, and just making the glass, because as I'll wait for the Q&A maybe, but we get asked every once in a while, like, is any of this glass reused? Are we sourcing this from something else? Is it a rehouse? And it's not. It's absolutely not. These are all new glasses, and so we have to worry about if they're manufactured correctly to our spec, if they meet the surface figure. There's a few things on the surface figure that are not good on this. So it's sort of like I never really want to show anything. I used to be a very strict perfectionist where I'd rather smash it than, but then it's like, but no, not today. That's the old me. Definitely I won't smash a lens, I promise that. I've never done that. I'm talking about like paper and stuff. Okay. So you're going to see some cool like Petsful stuff. Can I get another subject or someone who'd like to come to the front?
Screen.
This one will be less. Max, thank you. So this one, yeah. So we don't have focus perfectly tuned in everywhere. We also have some uncoded stuff going on. But if I can let's see if I can get this happen. But what you're going to see, if it's evident, is a difference in the style of breathing, which is going to contribute to sort of a vertical change of field of view and no longer that horizontal field of view. And again, this is a 47 millimeter. This is the first one. We're going to probably increase its close focus. Somewhere in here is where we're at right now. And then sort of I'll just do a side to side. There's a lot of, I call it sort of swimming distortion. Again, another thing we're probably going to change on it. But I figured rather than wait to show, which could be a few months down the line, we had the opportunity to bring this, and we really thought it'd be something special to share with you also. Max, thank you very much. Thank you for letting me. Oh,
yeah.
Yes. Hajun, can you help me with the flare? So you'll see some of these diagonals coming off, which is the astigmatizers doing their job. The colors and the profiles of these flares are subject to change, but like I said, everything with the prototype is subject to change. You can see some of the surface figuring and showing up inside of the flares themselves. Thank you, Hajun. It's really cool. So beyond these things, I think we're pretty good on time. We're good. I think it's good to open up to Q&A. Yeah. Oh, actually, let's do Q&A, and then we'll end we have a special slide at the end for you guys.
Yeah.
But we got to do Q&A first to get there, so we'll do it as things get boring here. And first off, thank you all for coming again.
You said 55 minutes, and it's or 55 after.
Yeah. Do we need to get mics, or are we okay? Awesome. Yes.
Hello.
Hey.
So I remember from the last year that there was like a discussion more elaborate on the, how would I say, characteristic of each sensor is different because it has like tiny optics itself.
Okay.
Do you ever test for different cameras is there like some sort of a goal to make it work for like broader spectrum of sensors? Or is
Yeah.
it all, I can imagine, tested on like high science laser things. I guess
Yeah.
they will tell you like every optic characteristic about the lens. But is there like any of this testing?
Th- That's a good question. The factor I think that comes into that would be like the pixel pitch of that camera, and they do change depending on it. Like the 8K sensors that sort of came out with red and had a lot denser pixels, and so I think those went under, let's say, 5 microns. That did change sort of our goalpost a little bit, because if you had lower density, the original Arri, like Alexa, I think was always like about an 8 micron pitch, a little bit bigger than 8. And so those things factor into, okay, well, if as long as you're hitting that metric with your spot diagram on Zmax, then that might be where you end your optimization. Why would you bother trying to go underneath a pixel density? Because at that point, you might end up just getting Moiré effects and stuff. If you guys ever seen Moiré, you're just basically challenging that at that point. Or
Information that doesn't exist.
information that can't be captured.
Yeah.
But because of bigger sensors or denser pixels, photosites, yeah, it absolutely matters. And then I think also then there's also that sort of creative, let's say like the look of it that you're trying to go with. We'll also let it taper off. So I kind of would say somewhere around that 8 micron, 5 micron area, sort of a sweet spot that is very, very well corrected. And so if you hit what you want there and you're happy with the compromises you've made in your design, then overall you have a well-rounded lens. You could start with that.
Yeah, thank you.
Thank you.
I mean, generally, the pixels get smaller than 4 microns, they get noisy. So there's a trade-off of pixel size versus the noise you have to correct. So it's kind of a theoretical limit.
Yes. Let's see, we have one up there. Yeah.
My question would be, is the design of the flaring, is it more a technical decision or a creative decision? How do you approach these things, and how much time and effort do you put into the designing of the flares?
It's half of it is sort of consequential of the design because we're working for the optical design first, and knowing that certain surfaces are going to be coated differently, we always choose to coat the cylinders differently than the spherical glass. So a lot of the horizontal flares and the things you see are coming, bouncing off of those cylinders. The color is sort of an aesthetic choice.
We've got special coatings that we've designed ourselves.
Yeah.
Give us the amber flare, for instance. We also have some modeling where we can do. It works pretty well, but if we see a cylinder that's not doing anything as far as flare, then we'll give it a good AR coating so that it gives us light transmission. No sense putting a 2% reflecting coating on a surface that doesn't create the right flare. So it's one of those things that it's a combination. We can't simulate everything because it just takes too much computer time, but we can get the colors what we want, and we can figure out which surfaces do the most and make it that way.
Yeah, in a technical sense, the single-coated flares, or they're not even single-coated really, but they emulate the single coatings. The point is you want to achieve as much transmission through the glass as possible, so on a technical merit, that would want you to force total broadband AR coating, which would be just basically no flare, so something like akin to just a perfect lens that has no flare absolutely would be the best transmissive lens you have, so your T-stop is going to be higher. If you allow some surfaces to be near single-coated, you're losing some light, but at the same time, you're gaining a little bit of that kickback. You're gaining back some of that character from the flare. And then, we do colorize it based on it's choice. It's essentially sort of what do we think this lens needs. And so something new like the Gemini, you guys are kind of witnessing it real time. I imagine there's we have probably all varying opinions about what it could be in the end, but it's so new that it might be something different than what you see on camera.
Remember the A through G series at NAB 2 years ago? We had made the Orions with a bunch of different coatings, the pink one.
Oh, yeah. We've done some experiments for sure. I don't know if you guys have seen, but if you ever come to Atlas in person, we have purple, pink. There's lots of like cylinder coatings we've done.
It's great for the Barbie movie.
Yeah, there was one that's like hot pink. That's like really fun. Question here, Max? Yeah. That's the only one I know right now, I guess. Yeah.
So you mentioned you don't know the coverage that this lens is going to do. A lot of new cameras now, the Fuji Eterna, 17K, Blackmagic, going 65.
Yeah.
Are you looking at potentially having that large of a coverage for this lens? Or?
It's a decision that drives what the product is going to be and who it's aimed for and what we want it to be used for, I guess. And so, yeah, it's not a decision that we've made yet. And like you said, it's almost only recent that we're hearing about a lot of these newer cameras that are going to be above full frame. So why not consider it, you know? And I think we're early enough to where we can figure that out. Yeah, so it's hard to say. I know as much as you do, Max. I haven't. Yeah.
Thank you very much.
Thank you.
Well, I thought we'd have more questions.
Are you done? Oh, all right. Yeah.
Oh,
Don't ask. No, I'm just kidding.
Hello again. And now I would like to ask, from the different side of the lens, as of the front, do you also test, right now I'm speaking regardless to the new 18 millimeter extremely wide, the Orion.
Yeah.
Do you ever take in account of like the front glass filters that people put in?
Oh. Do you?
What are you talking like ND filters?
Like, well, the ones that change sort of the, like, Pro Mist, that kind of thing?
Yeah, I think so. Like, especially nowadays when, like, I would say generally film immersion or like emulation is, I think now, like, the pretty common, I would say. And that involves, like, all these filters.
I look at filters from my understanding. It's sort of, if you put it in front of the system, it's going to behave quite linearly. It's kind of like addition versus multiplication. So we don't really take it into account because it's always something you could add, you know, and that's, so the strength at which you want to put in front of a lens will be, and I think that might be different on its the entrance pupil.
Now, mostly it's the angles of light on the 18. The light's entering at 130 degrees.
Yeah, that
65 degrees from the optical axis. So it's going through 3 times as much of the filter. The air coating's not in the right band. So there's a lot of things that you may need a filter that's optimized for a wide-angle lens eventually.
Yeah, so definitely we didn't consider on something like that, and we probably wouldn't just because with something that wide, we're barely able to get it through its own shroud. Like on the 25, if you see the way it's cut out, it's just it's a necessity for that coverage to happen. And so in that case, those are sort of, you'd have to have really large filters, or like as you said, such an oblique angle, you're probably not using the filter as which it's designed for. But for like a 65 or something, let's say, we really just focus on the base look of the lens that we want it to look like first. And then I do think about it because people have told me they shoot with a certain filter on top of the Orions, and they enjoy the look that they have that comes out of it. And but I just look at it like in addition to, you know, just something to add on, and you can quickly take away. So.
And so you never like thought about getting into making your own filters?
Not at that. Yeah, I haven't thought about it. Yeah.
Thank you.
Up there.
Yeah. Oh yeah, at the back.
At
the very top.
Yeah.
And if that's someone else.
Taking off the lights on.
Hi. My question is about, have you considered spherical optical design for your lenses, in a meaning of more ecological and smaller form factor replication of anamorphics? Have your optical team calculated some variants, some options that could be achieved through the spherical optical design?
Mm-hmm. We look at that. one of the things that we do in-house, just to share a bit more like behind the curtain, is we do a lot of design studies, and we do take different pathways, and that door is open looking at spherical, and spherical essentially primarily that does focus on capturing some of that feel from Anamorphic and bringing that with it.
Sirius series was 3 years ago, 2 years ago?
Yeah, that was sort of
we had actually modified, essentially take the cylinders out of an Orion lens, and it was a surprisingly interesting design. It was very Petzval-like, and there may be somebody who wants something like that for a project, but you know, no, we experiment all the time. Think of it that way.
Yeah, and there is application, I think, for the use of such a small lens that can capture, you know, let's say sort of the essence of some of the anamorphic part of it.
Without being anamorphic.
Without being anamorphic. But nothing in the pipeline, you know, directly right now that I can tell you about. But it's certainly something that we do look at and experiment with.
Yeah, my question was a bit more, if you look at it more from engineering point of view, not from salesman, and if you will talk about the look that could be achieved, because lenses is a math, so have you calculated some possibilities to make spherical lenses that will achieve some better qualities than anamorphics in a smaller or lighter form factor, with the keep of this look that we're talking about, maybe not flares, but about distortions, about some additional aberrations and some depth in an out of focus area. Thank you very much.
All right, thank you.
May I the last question or not? Here? Hello?
Yeah.
Oh, sorry.
We have another hour, don't we?
No, I think we're out.
What?
Yeah, one more question then?
Yeah.
Oh, there we go.
Yeah.
Yes.
Okay, my question is quite crazy, but maybe this is the best question for you, because I see that you have dreams about constructing something really new and impossible. So my question is, if I'm doing a movie and the budget has no limit, and I'm asking you to make the lens which has possibility of regulation of the flare, softness, breathing, everything in one lens, okay? And the budget is not a problem. Do you think it would be possible to make this kind of lens? Let's say it will be 35.
All right, so repeat back. The no breathing is one of the characteristics?
All factors, like color of the flare, whatever is inside the lens, and I can change it in one lens, physically.
Oh, okay. Like
Can
an
you
inner...
self-detune?
Yeah, whatever.
It depends how much of it, how much of the look you're trying to change in one lens. Yeah, we could definitely discuss that back and forth. Like, give me some hypotheticals that you'd want. I could tell you how realistic that would be. It's easy to figure out. Like, if there's certain things that you would have to probably change a group entirely. You know, like reinstall it, so you're essentially building a new lens or a new group of the lens. Sometimes you can reuse the same cylinders if you're just trying to change a few aspects, but if you change too much, then you might have to change the cylinders too. Right. So you almost, in a way, are making a kit lens that does a lot of different things. But the primary constraint of lens design is that it's kind of, you know, and this is the way Scott's described it, is it's sort of a balloon that you can push on. So you can try to squeeze these aspects and try to correct for them, but then it's going to try to pop out somewhere else. And so the whole nature of lens design is a compromise. You can do things like add A-spheres and other things to sort of give you an advantage. And we generally haven't wanted, or we haven't used them, but for the looks that we've created. But I think all things, definitely there's
You said unlimited
a road to
budget, so.
Huh?
You said unlimited.
Unlimited budget, a lot of things are possible. Yeah. It just depends how much you want to do.
This is exactly my question. This is more philosophical question, that you're not thinking about the budget to sell the lens, but to make the lens.
Yeah.
So this is about your dream, not about the money, yeah?
Yeah.
Because I'm not interested in technicality. I'm DOP, but really I'm very weak about all this diagrams, mathematics. Always I'm checking the look of the lens on the screen, and this only matters for me. So this kind of lens would be amazing. Probably this is impossible, but maybe it's possible.
Yeah, I think it's possible.
Enough money, probably.
Yeah,
possible.
I always try to translate what you're describing, which is you know what it looks like, what you want.
Right.
But for me to know, to give a proper answer, it will come down to converting those into aspects of design, and that's
Design
what we're pretty
parameters.
good at doing. So, like I said, with enough back and forth, we would definitely get to a point where I could tell you this is what it is. And yeah, in this hypothetical scenario, money is not something I'm talking about. I'm just talking about the sort of first principles that take me to give you the look that you're trying to talk about. So if it's something like you said, I want zero distortion, and I want no coma, and I want no lateral color, and I want this, you might be talking about a big old lens, and at that point, then it's like, cool, and you might be okay with that because it's hypothetical. It could weigh 500 pounds, but that would be okay. And then if it's like interchangeable, yeah, there's probably ways to do that too. I think all those things just come down to what happens is like the real world is
The laws of physics and
yeah. Oh, and what you can carry and what you can
Yeah,
lift on a
steady
camera
camera,
and what the
500
mount
pound
can
lens, yeah.
sustain. And so those factors only come in towards the end as you kind of come back from big scopes or the dream world back into how do we make that a reality. And so that's sort of been my niche, is trying to focus down on I never tried to even in our own ideas, it's important not to ever dismiss a new idea. It's important to try to really obtain an understanding if it's possible, because I really think if you feel strongly enough about it and your gut kind of leads you towards an answer, and eventually you have to match that with science and physics, and that's sort of my favorite part about it, is that you can back it up at the end of the day. So in your scenario, it's definitely possible. You just have to find that way. Yeah.
Anybody else?
We have more time, by the way, I was thinking, but so if there are any questions, feel free. Yes.
Oh, one more.
Thank you, Mr. DeWald and Mr. Schultz, first of all, for taking the time to do this seminar. My question isn't necessarily about specifically the Orions, but more about anamorphics in general, and about the anamorphic bokeh that is obviously it's oval shaped. However, if you de-squeeze an oval, that would become circle again, right?
Mm-hmm. Right.
So
right.
Is the do they stay after the de-squeeze? Do the anamorphic bokehs still stay oval because of a physical trait, or because of the de-squeeze software?
That's a great question. That something that Scott and I just recently discussed, which is, to keep the math simple, like a 2x anamorphic, you still get 2x bokeh after the fact that you've de-squeezed it.
Right.
It's because on the sensor, you're actually receiving sort of a 4x bokeh. So when you de-squeeze, and that's due to the fact that the depth of focus?
Well, the focal length is different by a factor of 2, and the depth of focus is different by a factor of 2, and those two work together
the
to
two,
be 4.
it's like a squared.
So it's a very thin oval on the sensor, and then it gets squeezed back to a 2x oval when you de-squeeze. Yeah, I know it's not very counterintuitive.
It's not too, but basically the depth of focus is squared, so you end up with 4. So when you do de-squeeze, you have bokeh that's a 2x ratio, and that works.
It's a good question, though.
Yeah, and it's a great question.
I didn't believe that 5 years ago either. So,
Thank you.
Right,
When designing the lenses, how much of the flow of light would you say is computer simulated, and how much is done using classical math, essentially?
Scott knows the program pretty well. Do you mean within the confines of ZMAX or our process
within
of doing
ZMAX.
it? Okay.
Probably 90% of it. Yeah, I mean we like ZMAX because it's got some nice graphical output, and it's pretty intuitive user interface. But believe it or not, we're probably one of the only anamorphic companies that uses that program, I think. All the German companies have their own software they wrote themselves, and same with the Japanese. So.
Yeah, and to further, I think because I was asking Scott this too, is like the math used behind it are calculations that are made, but it's actually tracing incrementally or sequentially, right? It's, like you said, it's walking along. So the rays are actually being projected through, and then it's figuring out as it's doing it. So it's actually tracing the rays.
The rays step along in space until it hits something, then it kind of figures out exactly what the interface is, then it figures out the angle of incidence, does the refraction, and then goes to the other surface and to the air.
So the code kind of works in tandem.
Happens 8 million times a second, something like that.
So has the recent surge in like ray tracing software and hardware been very helpful for your project?
You mean like the rendering softwares?
Yeah.
Not really, because they don't really show us mathematically the aberrations like in those little plots we showed you. Because I can look at one of those and say, I need to split this lens, I need to make a doublet over here. And you're not going to learn any of that because you don't know what the errors are. You're just going to see the result of those errors, I guess, by the blurring, color fringing, what have you.
Yeah, I know that there are a few things like that came across my table, like the stuff in Blender you can do now where you can actually set up a lens and put the same radii through. So if you have access to, let's say, the Zmax design and the spot diagrams, and you can actually recreate some of that stuff. I only got as far as the lens, but it didn't have dispersion, so I wasn't seeing color. And so I only got as far as like a few setups in Blender. And what I want to do is get back and actually recreate that whole spot diagram I do in sort of an infinitely spot laser, as it was described. Which a spot diagram is basically, just to explain, is an infinitely small point far out, or at any point that you want to position it. Usually you start at infinity when you do lens design. So just imagine a star, and how is that star focused? Even in a perfect lens, there's going to be some factor of a point spread function because of due to diffraction. But beyond that, there's the aberrations of the lens itself. And so you can recreate that both by ray tracing and Zmax, and then, as you said, in a computer program that can do it. But they're just not easily set up to quickly budge around parameters. In Zmax, it's just so much easier to move things and quickly get an update. It feels like it took me years just to like get the stuff set up in Blender, and I'm like, and it's how Blender is meant to be sort of imperfect. So if I'm like, did I accidentally move that? There's no way to like check later, and I gotta. So once we build a system out a little bit better, it'd be fun to simulate both in 3D, because I do think that would be great. Because in Zmax you can do image simulation, but it's done by creating a flat plane, and you can put whatever image you want onto it. So you can recreate like a focus chart. But what you can't do is recreate sort of the human face or something like that. Like a 3D object would be really cool.
Thank you.
Haji, any stretching, or you got a question?
Yes.
All right.
Hello.
Hey.
So I obviously work with Atlas. For context, I'm the executive assistant. But for me, when I first joined the company, I really believed in the company goals of making cinematography more personal and rewarding and unique. And one of the things that I really appreciated, especially when I was a student, was the accessibility aspect of how these lenses were made to be available for the general public, especially during the start of the company. So with that context in mind, I was wondering, in the engineering aspect of the lenses, is there any point in the development that you have to either compromise or even go potentially like lean towards more in the development process to help and support that aspect of making these lenses, or if there's anything that, if we want to achieve, let's say, for example, 0 focus breathing or something, it's going to be infinitely more expensive and all that stuff. So are there any technical challenges that you wish you could do, but or if you can do and all that? So
yeah, there's things like distortion or certain characteristics that maybe it'd be preferable to like push back against and say, oh, can we reduce this? But then what you see is the size of the optics increases, right? And so then either the weight of the lens is going to increase, the size of it's going to increase, and all of that's going to add up to, like you said, a little bit more cost. Or it just might become to the point where you might not want to manage that. It might not be a popular size to just say, hey, this lens is going to be as big as possible. And so on a technical merit, you might want that, but then you have to say, is there a better way we can achieve it, or is there a compromise that we can come to? And I definitely think every lens that we've done has come through that. A little thing about the Mercury is that it's much smaller, and people comment on that it's much smaller than Orion, and partly that's to do with the different focus method. And some of that things has actually increased the way that we were able to correct color for this lens. And the other reason, though, that we were able to keep this small is that it's not a 2x squeeze, it's a 1.5. And that also helps sometimes in those areas of correction. And in terms of like making it more accessible, it's sort of a balance between how far can we push the size, how far can we push the design, and manage those expectations of like how fast is it going to be. And that's another thing too, I guess I forgot that one. That's like the biggest one. Like everyone would love a really, really fast lens all the time, but then if you design it to be fast, you might design yourself into a corner where it's only going to be good at one thing, and it's going to kind of be, mediocre. Even if you stop down, that same lens will not correct the same for a lens that you've corrected for, let's say, 2.2. So yeah, I think all around, we're surrounded by sort of the reality of, is this good to do, or are we shooting ourselves in the foot?
And performance and
close focus is one thing I always really, we go back and forth on that, because it's like, how about we do closer?
And of any three of the four.
Exactly. I always want closer. So,
all right.
Thank you, Haji. That was a good question.
Oh, right here.
2? Is there one in the front, and then?
Chicago Bulls hat.
At the top.
You mentioned about Blender.
Mm-hmm.
So did you just use the materials you applied onto the curvature and thickness of the lenses, lens elements, and then did spot tracing? I mean, ray tracing to create the spots, right?
Yeah, I used a setup that was used, I can't remember the name, like the optics plugin, I think, was what got me started on it. And a coworker of mine had already applied a material, and I went in and sort of tried to understand it. I can't say that I fully have grasped everything about if that material is sort of existing between the two surfaces, or if it's just happening at the surface. And I'm very much new to that whole thing in Blender.
And then Blender just used the Ebbe number, right? It didn't have the full
It
dispersion
didn't.
curve.
I wasn't able to get the dispersion.
Yeah,
so or I had the
there's a lot of stuff about modeling the glasses that I don't know if all that information is in Blender, because the change with wavelength with frequency is it's nonlinear, and it's hard. It's curve fit, and there's a 5-degree polynomial that they use in ZMax that probably isn't in Blender. So I don't know.
Did you just successfully reconstructed the spot? Did you get what you want in the end?
Not yet. I got to the point where I had white light going through it, but I wasn't. When I started playing around with it, setting up colors, I was just getting weird, like a red image and a little bit orange image, and I thought I'll try to figure this out later.
You must have just used the laser source as a light source to shoot the ray.
Possibly.
But you didn't do path tracing.
I'm not. Yeah.
Okay.
I'm not
I tried
sure.
the same, so I didn't get anywhere. So.
Oh, okay. If I find out,
it's not a design program.
Hit me up later. I'll tell you when I get the right answer. We'll work on it.
That would be great. Thank you.
There he is.
Hello. I have a question. What was the first focal length of the Mercury series you designed, and how many prototypes you make it before the final form?
That's a good question.
Yeah, very good. That was the 42, and this would be, if we count both optical and mechanical iterations, this would be the 4th prototype, or the 4th prototype became the
fourth generation, I guess you call it.
Yeah, 4th generation became the production version. Early on, we had things like the rear optic was sticking too far back. in the very early iteration, we had a little bit too much unwanted side-to-side distortion, which caused it to look like a change of squeeze, which is just probably a little too much for the field of view we were getting. A little bit of that's okay when you get towards the wider end, but for the 42, we had to mitigate that. So this would be number 4.
Okay, thank you. So the first one was 34, and the last one will be?
Oh yeah, first one 42. Last one will be yet to be announced, but certainly the 27 is brand new, but it's not the last one. Yeah.
Cool, thank you.
Mm-hmm. Yes, we have one.
Because we got a lovely prime lens from you, but I would like to ask, do you consider doing a zoom anamorphic lens?
Yeah, totally.
Can you spoil something?
I could say, this is open session, so yeah, you're behind the curtain. We've looked at it for quite some time. It's sort of an on and off thing that we'll do because the priorities of, like, let's say the product line of Mercury sort of gets to the forefront, and then all of our engineering and R&D and studies kind of go back to working on those things to get those produced. But then we'll go back into the studies that we've been doing for zooms, and so we've been trying to accomplish something that we think everyone will ultimately grasp onto, because it's like a matter of how big do we want to make it, what zoom ratio can we do, what t-stop do we want to do,
it's a lot more complicated than a fixed focal length.
Yeah, we're going to get to a point when once we're happy with the internal study that we have, and it gives us a good insight into we should probably do it this way, that's going to be the day that you'll probably start hearing a little bit more noise about it. I could say we're a lot closer than we were last year when that question was asked, and we've done a lot since then to get to that direction.
Thank you very much.
Thank you.
Hello. The question is, do you think about to get some metadata out of the lenses, especially for VFX?
I think that's it's a great question. More recently, I've been thinking about that personally, I would say, and thinking about incorporating that, but I don't think I've told anyone in the company that. But it is something that I think is achievable. We could probably end up doing, because there's just so much more reason to need to do that, especially in the production environments that they're doing now, with so much more virtual, a mixing of the real and virtual, and I think that's where it really kicks in, right? Because you want to have every focus move recorded, and I think that there's value in doing that. Yeah.
Thank you.
Oh, a question up there, and over there.
Here.
Yeah.
How much thought goes into durability of the mechanics and optics, like the longevity of the lens, if it holds up for 70 years at a rental house, or?
Yeah, that's kind of one of the first things we try to figure out, is sort of design it backwards and understand, like, how do we want this lens to be built, let's say 10, 15, 20 years from now? How do we want people to think about it when they're using it? And one of those things is it better exist, right? Like, it shouldn't be broken, things shouldn't wear down. So where do we put the friction points? How do we make sure there aren't too many? What type of grease do we put into the lens? And those are...
Ease of disassembly for service.
Serviceability. Yeah. For the things that we know just can't last that long. But I mean, I think, generally speaking, a lot of the lenses do last. If you use the right materials, if you use the right grease, it stays in the right channels of the lens. That's a big consideration that we have. And once we've captured that, let's say like in the Mercury, then it's a lot easier to translate that same design philosophy over to the next focal length. If you mimic the same sort of internal areas of the lens. So we do give it a lot of thought, and that takes a long time during the initial phases, and sometimes it's experimentation. And there are times when you're under the gun and you don't care, and then I just like, let's do it. So if I focus that lens, it just feels like I'm just grinding on stone, but I can promise I'm not, but it definitely feels like it. And that's okay for a prototype. We'll learn and we'll figure out why did we do that, and can we do something better next time? Reduce the surface area or something of how components are touching, that kind of thing.
I have a general question about producing a lens. Where do you see improvements could be made, or in the production line? Is it difficult to get the parts? Is it getting the right tolerances from the parts, or are you having difficulty getting the right glass? Maybe could you talk maybe more broader about
like
producing a lens, the challenges? Yeah.
Of producing, yeah.
Yeah. For the last couple of years, there was a kind of a shortage of a lot of glass types. And I think we kind of didn't we get held up on one of the Mercuries for a while because it was one of the glasses wasn't available because there's still it takes sometimes 6 months to make a ton of glass in a glass melt. So if the factory shut down, everyone's scrambling to find an equivalent glass and wherever they can get it from. And when it's gone, and you got to wait 6 months for somebody to make some more again. So yeah, that's an issue, and that's why we did the pre-built orders, right? Where we would like we did in the Orion case, right? People could pre-order them. We knew how many to order. We knew how much glass to order, and it's that way that glass is available when we needed it. So
you want to
managing of the supply.
If you have the advantage to buy the glass up front, and then you want to do that because then, like as Scott said, even if there's a shortage or a batch can't be run, you've already acquired what you need to at least cut the glass out of. But I'd say definitely challenging. The glass is always getting it produced correctly, and then having a yield, like a high yield, especially for cylinders. They're going to be more challenging at the manufacturing state level, and that's sort of one factor that goes into it. We're trying to currently manage a lot more of that ourselves so that we can sort of lift those burdens of being reliant on, let's say, like a slowdown, or let's say it's like if we can control more of that process in-house, that we can sort of overcome those hurdles. So if you can sort of, this is just like supply chain philosophy, but if the more that you can actually have a direct impact and control on it, the easier things might go. That's been my experience. I used to come from that, where it's like, I'm very, like I said, just sort of, if I know I can do it well, I'll just do it myself. But there's other times when you're new, you're just starting, you have to rely on the experts, you have to rely on people that have been doing it. But
well, our design philosophy didn't require state-of-the-art tolerances either. I mean, that's we designed the lenses to be not needing the highest level of precision tolerances because each element has less power.
Yeah,
we could use a standard, what you call they wouldn't call it a poker chip design, but the barrel. A lot of this stuff is more simple because we designed it originally to be mass producible, and we don't have to do any special centering or anything like that when we're assembling the lens.
Right. So part of it is figuring out beforehand. Don't design yourself into a hole where you say, okay, I have a really tight tolerance on all of these surfaces, all the centration has to be this way. Then you've really kind of shot yourself in the foot before you even got going. And as Scott said, we did the tolerance analysis to make sure that there's not one particular element that's going to throw us miles off, like when it comes in terms of calibration or something. But the struggle is real, like making stuff is hard. I think everyone is willing to admit that, whether you're doing it all yourself or you're, like we're not grinding the glass fully yet. We've done some in-house stuff, but we're not fully making like all of our elements from, as we said, the bulk blanks. They get cut down, then they get cut to size, then they get ground to size. That's a process by which we haven't pulled that in-house yet, or the coding of those elements. But it certainly would be the dream, because then you can sort of impart changes in line, right, that you ultimately would be harder to do if you just don't have control of that process. But because that's a big part of the makeup of the lens, that's one of the most challenging parts about it. Yes, and yeah.
Hello, I would like to ask you how hard is to make another focal length? Like, I assume you start something on mid-range, like 50, and you come to narrow or longer lens. So do you have to like change completely internally for some focal lengths? Like, is it that complicated?
Yeah.
It's complicated, but they're predictable. There are just to share, like, with going more telephoto, let's say, let's say that we're leaving the aperture the same. I'll just say T2, just to say, let's say we're doing a T2 lens and we had a design for a T2 50 millimeter. If someone said, okay, now let's design a 90 millimeter or an 85 millimeter, I know that the entrance pupil or the size of my optics up the front are going to be a lot larger. They're going to induce some, if there's focusing happening there, that's going to induce a lot more spherical aberration. But I know the opposite with wide angle. I'm going to be really concerned about field curvature and distortion and coma, and so I'm going to focus on different attributes of aberration and worry about correcting them differently. So as you start to experiment, or as you start to or as you just get experience by designing these types of different focal lengths, you'll start to see sort of the repeated
similarities between the wide angle.
Yeah, similarities between wide angles and similarities between telephotos and why they exist.
Solving the same optical problem. And
right.
They generally look the same.
Right, and in that way, I wouldn't say it makes it easier, but it definitely gives you the right direction. So it would be so much harder if you weren't using that sort of advantage of like a starting point. But yeah, it is tough to just sort of say, all right, take a 50 and let's make like a double the focal length. It might not look like the same lens anymore, and that's probably a good thing. If it looks really similar, you're probably not like changing enough things to get to that such of a big jump. Yeah.
That is probably second part. I would like to ask how you maintain the same look of the series.
So that would be down to how some of the charts that you saw, like where it showed like the ray fans and the actual performance metrics that we're getting in the simulations, or
we do the optimization. We have parameters that we maintain throughout the whole series of lenses. So
yeah, is it still on? Let's put the Zmax back up. I'll put the computer on. I won't take too much time, but you brought up a good point.
This is cool stuff.
Yeah. So I'm just I'll just pull up the spot diagram.
Well, no, leave them both up. But
yeah. So you'll look at different field points along your imager. These represent just areas along the imager. Oh yeah, sorry. I thought it was up.
Oops. Oh, you got to push the projector button.
Let me see. Let's see.
Nope.
Can you switch it to the HDMI?
Oh, it just switched. No.
Oh, okay. Sorry.
Yeah.
Me assuming that it was already up. So in a lens design like this, like the 65, which super wide open, we're going to see some larger spot size, but I think that's good for kind of showing off where things kind of get crazy. This first one here is the on-axis, and then we have other areas. Some represent points along the horizontal, some represent vertical, and some represent towards the corner. There's two for the corner, I think. And to achieve a similar look, you might compare the level of correction you've taken it and the attributes of why you did that, and you would want to look and hunt for those similar attributes on other lenses. You're never going to get one-to-one, but if you can get the majority of the look, you can...
And if we stress the same parameters when we're optimizing, we get many times a very similar answer.
Yeah.
And there's a lot of similarity in the glasses that we use because they work. They give us the color characteristics, so we usually don't have to change a bunch of the glasses. We just have to change the radiuses and the thicknesses and the spaces.
Yeah.
But generally, the color correction comes from the glasses we chose, and there's no need to change them if we want to keep the same look.
Yeah, because you can start with a really good base, and then so if you move to a new one, there's no need to just change everything like I was saying, but there's the need to sort of change elements in the front and near the back of the lens that will allow you to basically re-optimize for a longer focal length. But then you can force it back. This I don't think we're not doing anything illegal here. Yeah, so this mirror function is kind of blank. I just wanted to pull this up. This is where you would put in all of your parameters. They're called operands, and you essentially weight them, and you tell the program essentially how important
each one is.
Yeah, how important each aspect of correction is. There's a default one that everyone can know because you just go to default, say you optimize for spot radius. One's okay.
which is not optimizing for MTF, which would make the bar chip pattern look the best. So you just can't blindly say this is the way it's going to look the best.
And I'm not going to change. We're not going to make anything better here, but just for the sake of doing it, like this would be, if all I had was the default merit function, it's just going to assume, okay, you want generic correction of spot size. That's not enough to impart like a specific look though. There's other weights and things that we use within the lens design to treat certain areas of the field as more important than others. So if I just do a general
if we try
correction,
to make
it's trying to make everything equally important, and that's not what you want to do. Like
if you were to try to make the corner have no coma and no lateral color, the rest of the lens would get worse. So
yeah, exactly. It's going to think the corner is as important as the center. And we know that we wouldn't shoot that way. It's not like I'm saying I need the corner as sharp as I need the center. I definitely have some bias, right? So you have to replicate that and put that into your lens design.
Every lens.
And everybody has a different preference too. Like other designers and other manufacturers, they might require a certain level that they're just not willing to go below that or above that. And so we've kind of found a look for the Mercury. And then we utilize that optimization program, or operands, basically the list of operands, which they're not here right now, but we use those as a starting point and then compare the metrics. So.
And sorry if I may last
yeah,
question.
Of course.
How would you describe, or even if you think that Atlas lenses have some kind of look, do share some similarities between series?
Between the series that we make?
Between Orions and Mercuries, if you could tell something like, yeah, this is Atlas lens,
Got it. The one thing that I noticed that sort of carries over between them, they're very different, but I'd say the through focus, there's a little bit of, I call it through focus, where you focus just short and past the subject. I don't know if it's just me, but I sometimes, once somebody does that, I'm able to detect if that's our lens or not. And I don't know if that's a spherical aberration.
I'm watching commercials and I go, that's a 50 Orion, because we know from the bokeh shapes on the Orion lenses, everyone's different.
That's a big tell too.
Right?
Yeah.
And versus on the bokeh shapes on the Mercuries are all the same. They're all the same perfectly.
Yeah.
But on the Orions, because of the effect of the diopters in front, you get distorted bokeh, and some look like teardrops, some look like diamonds, and I think the 40 is like the best as far as oval bokeh. So that's a characteristic. And if I'm watching a TV commercial or a TV show, I'll know which lens it is just by the shape of the bokeh.
Yeah.
Thank you very much.
Thank you.
I have another question. It's like a two-stage question, since lens making seems to be not just mathematical correctness. Is there a certain attribute you like to focus on more, be it like distortion, bokeh, lens flare characteristic?
Yeah.
What would it be for you both? What do you look out most? And then I would like to know, do you have maybe a lens that you really like with characteristics, which is like your benchmark, like because this lens has a certain look?
Yeah.
Do you try to incorporate that also in your lenses you're making? Do you have something like that? That would be interesting.
I'll let you go first, Scott. What do you think?
Yes. Yeah, I mean, all this stuff's important, right? Like we've been talking about, this whole thing's been a trade-off of size and cost and manufacturability and whatever the...
But for like a look, though, like is there a thing
okay, my
that inspires you?
My favorites are the 138 Mercury and the actually 135 Orion I like too.
Why do you like those ones?
The focus isolation. The 135 actually appeared sharper when we built a prototype than it did in ZMAX.
Yeah.
Right?
Oh, yeah, yeah.
There's something magical about that lens, and I'd like to see that being used more.
Yeah, I definitely have images in my mind when I'm designing that like are sort of the cinematic world, so like, or a shot from a movie. It's not even like the whole movie. It'd be just like one particular frame that I kind of keep in mind, and so that drives a little bit of the undercurrent when it's like, okay, I'm pushing towards something. And so for Mercury, I don't know exactly what it was, but I had like, it's sort of just like, it's almost like it feels almost like as well as you can remember your dream, you know, like if you can try to paint it or you could try to draw it, but you're not quite there. But Mercury has like always been this thing where it's 1.5.
Uh-oh.
And
oh, you went dark.
Oh, it's just okay, cool. Yeah. And the 1.5, it's okay. That to me it had to feel like it's ready to make a movie. Like that was just what I kept thinking of, and that included things like distortion. And I knew I would allow it because I knew it was like, okay, it's full frame, and I want to keep about this much. And so in ZMax, like the program that we were talking about here, you can also pull up like a distortion map and compare those, and then sort of what we'll do is put that into Fusion, you know, like DaVinci Resolve, and there's a way where I can actually map it, then I can recreate the distortion profile and make a moving image. So I get past that point of I can't just stay static and look at one thing. Now I can actually pretend like the lens is real, just for a little bit. And then it's like, is this the right amount of distortion? And the last thing would be is the focus fall off. So the Mercury kind of has all these sort of 3 ingredients that make it unique enough for me that it doesn't feel like the Orion, and it feels, oh, that's what I was trying to say, I forgot that. It's more than 1.5x. It's 1.5x in math and squeeze ratio, but if you look at it on the camera, you get a feeling that there's something very anamorphic about that. That's not just, I bet it, because I could tell you if we did it differently and made just a 1.5x, we could do it to the point where it wouldn't feel as magical. And there's a lot of little things in there that induce that. And some of that's the imperfection, some of that's the pupil distortion, and some of that's the geometric distortion. But everything that comes out of that is like, that's why I like these older movies that look that way too, because they're imperfect in the same way. And it's not like there's a book that teaches you why those lenses were imperfect. You can look back in patents and stuff and try to recreate them and put them in, but it still doesn't tell you, it doesn't teach you. You have to sort of learn and teach yourself that. And so the Mercury for me was like a very personal journey of trying to rediscover that. Whereas Orion's, I was very new, and I could only attempt to understand, and Scott knew better at that point. And so in a way, Mercury was my chance to sort of like move into what can I do with this too and work together. What's that?
Nothing.
So that was this sort of it became a very personal lens to me, is what I want to say. Yeah. Oh, yes,
Hi.
of course.
Yeah, thank you so much. I just wanted to ask, will there ever be longer lenses in focal length, like 200 more millimeter, or will there be any official extenders from Atlas that can be put on in case there were, yeah.
For the Mercury specifically?
Yes,
or?
for example, or for any of the series, I don't know.
Well, we did the 200 millimeter for the Orion, which is pretty new. It's so new that maybe it hasn't been seen a lot here. So there's like a 135 now and a 200, whereas previously we only had the 100. We have for the Mercury the 138, and
there's an extender for the Orions too, right? So
there's an extender that works for both of these.
Yeah.
So you can get a longer focal length even on the Mercuries now, but a dedicated longer focal length is probably something that we would consider, given enough
demand for it. Yeah.
Enough demand, and if it's like something that we feel is correct, we'll put it in there. Yeah,
we're getting close on time here.
No, I think we're okay. It's still good. Have till 3.
Do you dream in anamorphic? And then my actual question: have you thought about doing a gentler squeeze, like 1.3, but with the feeling of 2 stretch? And also, have you ever done any thoughts or developments with stills lenses or vertical or portrait anamorphics as well?
That's a good,
I consider the 95 Mercury a portrait anamorphic, so it's like a perfect portrait lens.
Yeah. That one can be used vertically and cover a lot of format.
Yeah, it could be.
already. That's a great, yeah.
About as for dreaming, I don't remember.
I've dreamt about the merit function has like infected my dreams and the math problems, and it hurts. It's like the headache dreams that you get where you're like, what am I trying to solve when you wake up? I did dream actually last night about NRD, which was, I've never been there before, and I went in there and said, this is a kill house, I'm going to die. I had a dream about like graffitied walls and neon colors, and people were like dragging across the floor, and I was like, what is this dream? But that wasn't in Anamorphic, though. I don't know. I can't tell. I do say that I think in terms of just a little silly aside that I've always sort of held on to is that because we have sort of binocular vision, right? Mm-hmm. We see wider than we do vertically. And so in a way, I feel like we already see the world in an aspect ratio that mimics the widescreen ratio. So that is already like halfway there to always wanting to see. Now, Anamorphic is, I think, just another layer of removing reality because you get the painterly aspects that we don't see that way. And so when you see a movie like that, it just immediately sort of takes you in. It's like the difference between looking at a picture and looking at a painting and saying, I just want to study this for a little bit. I feel like Anamorphic visuals do that for me.
Can I just ask a follow-up? I've seen a lot of application of the Orion 25mm being used in feature films in addition to other lenses like Robbie Ryan, which is quite an amazing thing. And it seems to be something that's picking up. The 25 is used quite a lot. And then I also want to thank you for your scarves. It's been the best merchandise at Camerimage for the last 2 years. The actual question.
Thanks. Can you repeat the question about the lenses being used?
Yeah, so Robbie Ryan used them recently, so he's got other lenses, but he used the 25mm, and you see it in a lot of other feature films, maybe perhaps because they can't get wide enough anamorphics, but been ostensibly using the 25 quite a lot, and people have been picking it up to the main set of lenses and using it.
Yeah.
And yeah, it's quite amazing.
Yeah, totally. We've always known that for some movies like the Orions are going to serve as sort of those in-betweens that just weren't available before from let's say the A set or whatever they're using for the primary shoot. But you get like the 21 or the 18 and you can get a scene that covers, you get the whole coverage of the room. And there's probably not many options elsewhere that give you that type of coverage. Yeah.
Thank you.
Thank you. Well.
Okay, I got a question. Are you planning to make even bigger lenses for large format, or in the opposite way to maybe anamorphic parafocal zoom, or even super 16 lenses?
That's a good question. What do you think, Russell?
Say yes. Say yes.
Yeah, that's the answer.
Yeah.
So we're going to do that, both directions, and I think that's important. We've seen the Mercuries being used on smaller format, especially on film, because they are film compatible lenses, and I think it's important that we continue that design characteristic and that we take it down to other formats that are also film cameras, so or even just PL.
I've seen, on this extent, pretty good results with the Mercury and film. Do you think it's possible, maybe in a small batch or maybe whatever, that can also do an optical squeeze for the viewfinder of some classic camera like Harry that have maybe 1.5, so the operator can see through a 60mm camera already the squeeze optically in the external viewfinder? You think it's possible to design a small cylinder for those features like it exists in the past for two pair? Maybe we take an old one, we swap the two glasses, and this is one.
No, totally. That part about it, I up until now, it wasn't something that I had thought about, but it's entirely possible and probably necessary. It's been a few applications where if someone wanted to use a squeeze ratio that just isn't so common, or on a eyepiece that just doesn't have that, it is perfectly achievable to do that, and I'd say the eye has a little bit more forgiveness than the camera, so you'll be able to use it and not care so much about if there's a little bit of imperfection. In fact, they can be much simpler for that reason, that our eyes are very adaptable. So.
Thank you.
I've got the next question.
One more? Okay, so we got to do one more. And
I've got the hey, how's
is that Max? All right. No.
My question is on 1x anamorphics. I've seen quite a lot of that recently, like Hawk and stuff.
Okay.
What are your thoughts on that?
Using like the aperture to shape, just to give the look of anamorphic?
I'm not exactly sure how they work. I think it squeezes it and then squeezes it back to normal, and that way you have, I mean, I have no idea, but it seems quite interesting.
Oh, the one with the elliptical aperture in it.
There's the mini Hawks, I think, but
hybrids, or whatever they call them.
I think it's a cool. I mean, I think it's a cool approach to something that makes it a lot simpler. Like if that's what you need, and you know, because you're going to get things like it's probably going to be much lighter weight. It's going to be. I haven't seen them personally, but I bet you have a lot more control over things, because when you start to impart real cylinders in front of your prime lens design, you immediately sort of burden yourself with now have to worry about the correction for these cylinders. So if you can take those out of the equation, you can do a few more things. My only thought would be that you might not get certain characteristics, which would be sort of your disproportionate geometric distortion. That's very common with anamorphic, and that's because you have a different squeeze ratio going on, and you de-squeeze that, and your distortion pattern is going to look different than a spherical, which if you have a 1x, you're not changing the squeeze in the computer anymore, and so it's going to be a bit more even in that way. But I mean, I think there's room for all of those looks. You know, it's important to keep all options on the table.
Thank you very much.
I'm going to put up our last slide.
Well, I believe that concludes our time and everything, and I appreciate you guys working through us with the little, technical things and getting all this. It's very new, so thank you all. Okay.